So we've determined that our mixture is going to partially flash in our column. So some of it will go into the vapor phase, and some of it will go into the liquid phase. All right. So once again, here's the schematic. Some will go to the top, some will go to the bottom. And so what we need to do now is we need to figure out the molar flow rates for each of these streams, and we need to figure out the compositions. Okay. All right, and so we essentially have 4 unknowns. And so if we want to solve for those 4 unknowns, we need 4 different equations. Okay, so we have n sub t, y sub t1, n sub b, y sub b1. All right, and so from Raoult's law and combining Dalton's law, we already have 2 equations. And 2. So we need 2 more equations. Okay? And so for those 4 equations that we need, what we're going to do is we're going to use a combination of regular old material balances and Raoult's law. Okay? All right, so to do this, what we're going to do is we're first going to do an overall balance. So we'll draw our balance here. And so we're just going to, we don't have a mixture going on, or we don't have a reaction going on. So for our overall material balance, what we'll have are A is equal to I minus O plus G minus C. We'll assume we're operating at steady state and that we're not dealing with any sort of reaction. Therefore, our input is going to be equal to our output. Our input is the feed, and for our output, it's going to be the bottoms plus the top. Okay? So here, we know what our feed molar flow rate is. That was equal to 10. But we don't know NB or NT. Okay, so those are all going to be unknowns. All right, and so I'm going to restart the numbering here. I'm going to call this equation 1. Okay, so that was our first material balance. For our second material balance, what I'm going to do is I'm going to focus specifically on species 1, the water. All right, and the reason for that, the reason I'm doing this is because I'm going to want an equation, or at least a material balance, that involves the mole fractions in there. Okay? So our material balance, we'll start off with this. Steady state, no reaction. And we're going to get inputs equal to output. All right, and so for our input, we're going to have the species 1 that's in the feed. And so the way we could write that is we could take our feed molar flow rate and we can multiply it by X1F. Both of those things we know. For the bottom stream, we could do a similar thing. Whoops. Or X, let me put the letter first. XF1, XB1, NB. And we could do the same thing for the top. Y top 1 NT. Okay. All right, and so in this equation, we're now going to have 4 unknowns. Okay. So I'll call this equation 2. So those are our material balances. And now let's utilize our Raoult's law equations. All right. And so from Raoult's law, for species 1, we know that this statement is true. Okay? All right, and so here, we don't know YT1, we don't know YB1. But we can figure out P, and we could use Antoine's equation to get P1 sat. So we'll call this equation 3. And then we could set up another Raoult's law relationship for species 2. And we could write it like this. Right, and once again, we don't know these mole fractions. Whoops, there should be 2. But we know total P, and we could use Antoine's equation to get P2 sat. So that's going to be our fourth equation. All right, and so as I said, we had 4 unknowns, and now we have 4 equations. And what we have to do is we got to solve all 4 equations simultaneously. Okay? All right, so it's not the easiest sort of calculation in the world. But in your computations class, you have gone over, how to handle these sorts of systems. Okay, so you could do it by hand if you wanted to, but for now, I'm actually going to go over how you would do this in MATLAB. Okay, and so if you want to solve all 4 of these equations simultaneously in MATLAB, the first thing you got to do is you got to rewrite your equations implicitly. Okay, and so we'll take equation 1 and we'll write it like this. We'll take equation 2 and write it like this. We'll take equation 3, write it like this. Oh, whoops, there should be y. P1, P1 sat equal to 0. And we'll take equation 4 and write it like this. What was xb1 P2 sat? Okay? All right, so we wrote our equations in an implicit form. The reason we did that is because that allows us to incorporate this into one of the built-in MATLAB solvers for solving equations simultaneously. Okay? And so at this point, you could do it once again. You could do this by hand using Newton's method or whatever, or Gaussian elimination. But in your future, you're likely going to use some sort of program to do this calculation. So it's good if we get practice on how to do that now. So you use MATLAB. You could even do this in Excel if you wanted to. But for now, we're going to focus on using MATLAB. Okay? All right. And so here's the MATLAB code to approach this sort of problem. Okay? All right. And so what this code is going to be doing is it's, going to take those 4 equations and solve them simultaneously. And so at the beginning of the code, it just clears your workspace, right? And here we're going to say, we're going to have a vector with 4 different variables. And these 4 different variables, x1 is going to be the n sub t, x2 is n sub b, x3 is yt1, and x4 is going to be our xb1. Okay? And so in this code, we're actually going to have 2 sets of code. So the first part is we're just going to define a function which I'll call root 4D ICP3. Okay? All right, let's now go to that separate code for root 4D ICP3. All right, and so the way we write it is we define a function called root 4D ICP3 using the same variables here. We're going to define all of our knowns, so our NF, our XF1, our P1 sat and P2 sat, which we already calculated earlier in the problem, and then our total P, which is 7 kilopascals. Okay? And so, in this function, we're going to write a vector that contains each of those 4 different implicit functions that we derived. So f1 is our equation 1, f2 is our equation 2, f3 is equation 3, and f4 is that equation 4. Okay? And so once again, these are written in an implicit form. Right? And so what this function does is it just generates a vector that contains these 4 functions. Okay? So that's what this part of the code does. Let's now jump back into the other code. So we're saying our function is that root 4d ICP3. We're then going to define some initial guesses. So here we're just going to say our initial guesses for the molar flow rates are 5, and our initial guesses for both the vapor and the liquid phase mole fractions are 0.5. All right, now that we've defined our function and our initial guesses, in MATLAB, all we have to do is just call the fsolve function. And we just type in our function name here and our initial guesses, and we tell it to run. And once we do that, it'll then actually do that calculation where it's solving everything simultaneously. In our case, so I already ran the function, and it converged, and it tells us, or it converges to these values. Okay? And so, once again, this is n sub t, this is going to be nb, this is yt, and this is xb. All right? And so here, in our calculation, it converged to this. And so what I'm going to do now is not that, but I'm going to kind of box in our answers. So n sub t is equal to 2.89 moles per second. N sub b is equal to 7.11 moles per second. Y sub t1 is equal to 0.34, and xb1 is equal to 0.56. All right, and so from what we see here is that based on the conditions of our flash column, we started with something that was equal molar in both species 1 and species 2, and presumably it started off as a liquid, or it did start off as a liquid since the inlet pressure was 11 kilopascals, and that's above the bubble point pressure. Okay, so it is a liquid. But we see that when it passes through the flash column, the mixture is allowed to equilibrate at this new lower pressure. And what happens is that some of the mixture ends up vaporizing, but most of it actually stays as a liquid, right? And so we see that because the end bottoms has a higher molar flow rate than the end top. Okay? What we also find is that water, the initial feed mixture is equal molar, but in this vapor phase, the water is now has a smaller mole fraction, right? Now it's 0.34, while in the bottoms, or in the liquid phase, it's now enriched, right? So the vapor phase is water poor, the liquid phase is water rich. And that makes, actually qualitative sense, because if we go back and we look at the vapor pressures here, for P1 sat, or the vapor pressure for water at 30 degrees Celsius, is 4.25 kilopascals. And so that tells us it actually doesn't really want to vaporize that much. It wants to stay more so as a liquid. Versus for the ethanol, its vapor pressure is 10.56 kilopascals, right? So that tells us it has a higher vapor pressure, and so it's more likely to want to boil. It prefers, relative to water, it prefers to be in the vapor phase rather than the liquid phase. Okay? And consequently, we see that also reflected in the mole fractions, right? So more water is in the liquid phase than in the vapor phase. Okay? All right, and so, in this problem, this was a sort of kind of general approach to tackle these sort of flash calculations. Here, we assumed that our system obeyed the regular sort of version of Raoult's law, but you could easily incorporate the non-idealities in this step, where when you define your Raoult's law equations, you just also include the activity coefficient as well.